Okay, uh, today is October 16th, and welcome to the class of Solid Mechanics 2. Today, we will cover the beam theory as a continuation of a subject we covered last week. So we will review what we have learned last week, and then we will continue about the beam theory, mainly stresses due to bending or beam of the beam. Okay, this is the actually the chapter 10. This is the about the beam theory one. Uh, and it start with this stress distribution over a beam section. And there is a definition of a beams is a slender member, meaning that the length is longer than cross sections. And deformation theory, and the most important observation we start with this beam, this for the beam theory is the deformation. Well, you can say this is an assumption, but this is most likely what's happening in the beam. So let's say we have a straight beam, and then we apply the moment on the right-hand side M and left-hand side M. Now this beam will curved with a radius, uh, and obviously the top surface will be subject to uh, the compression, and the bottom surface will be subject to tension. Now, this is the equation describing the strain due to beam deflection assumption. So, okay, this is the parabol beam. I would say this long beam, but let's assume we pay attention to a little part of this one. Before deformation, that was like this rectangular, and this x is represent the longitudinal direction along the beam, and the y is the vertical directions. Now, under bending moment m, this will make the curvature with the radius r. Okay, this is a radius r. And there was let's say there is a line A and B before deformation and then after deformation. The strain uh, will be simply uh, before deformation, the length of before deformation minus length I mean the before deformation divided by the length before deformation. So this is gonna be the length, how much uh, uh, displacement. Okay. Again, the R represents the radius of the neutral axis. Well, we don't know exactly the neutral axis, but let's assume that there is a certain position that upper region will be a compression and lower region will be a tension. So this is a neutral axis, which will be determined from equilibrium. Anyhow, this R is the radius of the neutral axis. Now, this AB is which is apart from a neutral axis by y, and this AB will be deformed after deformation like this. And so after deformation, the length of A plus B prime will be, since this is R minus Y, Y is the height. So simply R minus Y times delta theta. Uh, Delta theta is the one, the angle created by these uh, curvatures. So del r minus y delta theta. Okay, I'm gonna use my laptop like this. Okay, so r minus y is this one, and then d theta will simply give us the length of a prime b prime. And then before deformation, this one length was like that. Now here is the important point. The length of a prime b, a and b will be the same as this neutral axis. This line and this line will be the same. So this line, actually the length of this one will be simply r times the delta t theta. So r minus delta t theta. So difference will be a deformation divided by the original length r d theta, and then simply r d theta disappear, and then this theta disappear. So minus y divided by r, and the 1 over r is let's say defined as a curvature, because the curvature, the more we bend, the radius will reduce. So physically, it's better to define a curvature. Curvature will be proportional to external moment. And very important point is that the strain, so this is the strain in y, will be given as the first proportional to y, and this is the curvature. Again, the curvature is simply 1 over r, and there is a minus. Well, why minus there? Because this is the plus zone and this is a minus zone, because y-axis like this. And the plus zone will give us the compression. So it makes sense. We just followed this assumption, and naturally there will be a minus there. Now, very importantly, the neutral axis, r d theta, okay, r d theta is this one. And actually, this r d theta, this is the assumed as the same as this one. And this one is simply dx. So r d theta is simply dx. So 1 over r from here, it can be seen here, d theta dx. So physically, d theta dx means that the angle variation, rate of the angle variation over the length, that is the r. 1 over r is a curvature. Okay. Again, this is very important. You can simply remember this one. And then a curvature can be easily obtained from inverse of a radius. And the so k, we have a k, and then we put it here, we get this one. Okay, this is the equation strain in terms of displacement or rotation of a theta. Well, there is a transverse strain, but at this point, that's not so important. So, actually, the beam, as we considered last time, we have a beam like this. Okay, something like that. If we consider widths. And the coordinate, this is x and y, and then this is the z. So we are applying actually the moment. Moment will create, this is the stress in x direction, right? Assuming that we don't apply any y stress and here, and we don't apply any g stress here. Actually, later we will apply the vertical load, certain distribution load or local load, but you will see the stress on the y direction is relatively negligible, very small compared to this sigma x. So uh, this give us, with these assumptions, the stress and strain, we have a very simple relation. We have a Young's modulus. Now, epsilon xx strain is already given as like this, or in terms of a theta, we have this. We just multiply E. Okay, so basically, this is a stress. Okay, this is a stress. I'm going to rewrite here. This is a stress minus y. As you can see over the y, is a proportional to a y coordinate, and then dx d theta, and then curvature. I'm sorry. This is the Young's modulus. Okay, so what is the unknown here? Unknown is simply this theta. The theta is simply like this will curved like this. This is the d theta. So theta we don't know, but as you can see, when we apply moment, okay, moment will generate theta, and then moment will generate the theta. So uh, right now, this is a stress, but we don't know yet about this theta. So basically, next step, we will drive the relation between this m and this theta. Rate of the variations. Well, again, this is not new. This is the subject we covered last week. The reason I'm doing again is that this is kind of a new subject to you, to all of you, and it is so important. Okay, so as we just mentioned that the moment and there is a unknown theta. And there will be relations. This is the equilibrium. Equilibrium. So equilibrium means that, okay, this is the stress. Stress, which varies through the thickness, I mean linearly through the thickness, and is caused by the moment. Now, so this stress sigma x will vary like this. So this stress will be equivalent to this moment. So this stress will be caused by the moment, or the moment resultant will be, I mean, the stress resultant will be the moment. So by definition of a moment, we have say sigma x here, and then I would say dA small. This is the dy, but we can say small a. So sigma x times dy will be the force, right? This is the force because the stress uh, times the area give us the force. Now the moment, how do you get the moment? Well, this force will simply cause the moment. So to get that, we need to multiply y. So that's why we have a y here. Okay, next step is very straightforward. Sigma x is simply like this. And then epsilon x, okay, epsilon x, we have to understand that we already know d theta and dx. Okay, so now here, very important. Now we are reaching or approaching toward the most important equation. Here we had there were y and there is another y here, and then these give us y square and Young's modulus and d theta dx. Okay, now if Young's modulus E is a constant like this, okay, constant like this over the area, this E will be out of integration. And this d theta dx, okay, d theta dx, rate of this cross section, what angle change, uh, will be the constant of the section. So this is the also out of integration. Okay, so what is the left is the integration of a y square dA. Now y square dA is the what? The geometrically, it is known that moment of inertia, IZZ, moment of inertia. And d theta dx, this is a d theta dx. We already went through this one. This is the given as the 1 over r. Anyhow, instead of this, we write the bending moment of inertia and the y. And now this is the equation. So this was the unknown. Okay, this was unknown. And now, given in terms of a moment we apply, the bending moment we can have from the section and modulus which is given. So this was unknown, now is given in terms of all known value. So this is the equation we obtain from equilibrium. Equilibrium again, the sigma x will give us the y, I mean moment. Okay, so the final equation, this is the same one, exactly the same one. But here, this is the one we just obtained or given in terms of a moment. And this was the stress strain equation. And this one was the strain from a deformation condition, right? Now, here, as we at that time we said this was unknown, right? Now this one is given in terms of a moment, so let's try to uh, put it back, and sigma here and Young's modulus put it here, and then this one goes here and this one goes here. So simply like this is stress strain and Young's modulus given here. And then this one moment divided by EI. And now here E and E Young's modulus disappear. So this is the stress we have for the beam. Okay. So it is a very simple equation and very, very fundamental result. In other words, we have a Young's modulus, we have a say H and the some cross-sectional shape of the beam, and then we apply the moment, how much the stress will distribute. That is the equation. Okay, moment, and this is a bending moment of inertia, and y. So y, okay, this is a maximum. What you need to do is that just put this height in y here, and then that's the moment, the stress we get. So this stress uh, physically, all the stress always is like the force divide the some section area, right? Section area. That is the physical stress. Force divided by A. Well, actually, this is the same. This is a force, and this is the section, cross-sectional property. In this case, the moment of inertia. And then it's a proportional to y, and we have a y. And for the actually, if we have a torsion, okay, torsion, we twist like this. There will be some shear stress develop. Okay, shear stress will be developed. Shear stress is also uh, look very similar to the bending stress. So as you can see that this is a torque, and this is a now polar moment of inertia instead of a bending moment of inertia. Polar moment of inertia is simply given r square and dA, and there is a R there. So as you can see, there is a very clear analogy between these stresses. This is a bending moment, this is a torsion, this is a polar moment of bending moment, and Y, and this is a R. Well, let's the, try to determine the neutral axis. This position relative to here or here, we didn't know. We don't know yet. When we drive equation, we just assume that this is the neutral axis. Now we can determine this. Where is this neutral axis? Uh, this neutral axis, the position of a neutral axis is determined by the uh, this one. Uh, well, we knew there is some axial stresses, but main point is that we don't apply any fx. Fx is zero. We didn't apply anything. Only apply the moment. So these stresses all cause this moment, but these stresses would not generate a resultant should be the zero. So this is of fx. And sigma x, we know this one, right? This is a sigma x, and put it back. And as you can see, this is a constant. And now the position of the this one, okay, this position has to be integration of cross section with respect to this is y, and it should be the zero. This is a definition of a neutral axis. Or this is very similar to definition of a center of a mass. This is the one. So any cross section and the y position should be determined. So the integration of y dA should be zero. So as we know, we this integration can given as the center of a neutral axis. I mean the center of a centroid, okay, centroid and cross section, and this should be zero. So which means that neutral axis always pass through the centroid. Okay. So, yes, it is a good time to review all the stresses due to force. Okay. Now back to the very beginning, one-dimensional bar. Bar is like this under the F. This is the bar. And the shaft is the same type of structure. And now instead of extension, we have twisting moment. Okay, twisting moment. Now beam, we have a beam like this, and this is the beam. Okay, so this is a main one-dimensional, I would say, structure cover in beam solid mechanics 1 was strength of material at the very beginning. Okay, so this was a bar, and this is a shaft, and this is a bending. And now, okay, this the name. Okay, this is the name of the member. Doesn't come from the shape of this structure, but name of the this structure comes from the force. See what kind of force we apply, then this member would have a name, bar, shaft, and beam. Okay, so the force we apply in the bar is the either tension or compression. In the shaft, we don't apply. This is we don't apply. And the beam, well, we do means that this is a vertical load. Actually, this vertical load will eventually create or cause this bending moment. This will be covered next chapter. So there will be a Fy and Fg. Means that this is the Fy and this is the Fg, and then a beam can bend like that, or bend upward, or bend sideways. And for the bar, we already know there is a no moment here. And the shaft, we have a twisting moment, and the beam, we have a bending moment. Well, so this is just a definition of this structure. Now, very importantly, let's take a look at the cross-sectional property for each case. The bar, okay, in the bar, the cross-sectional property, we simply, the cross-section equal integration of dA. And the shaft, the polar moment of inertia is the R squared dA. And beam, as we just mentioned, the bending moment of inertia is simply y squared dA. So all of these are related to, can be uh, considered as a cross-sectional properties. So stresses caused by this force with this cross-sectional property will be like this. Well, bar is simply sigma x force divided by A, right? And shaft, the stress will be a force divided by A. Well, I just say A because this is the same cross-sectional property, and increase along the R radius. And the bending, well, we just learned that. Oops. Uh, Moment of inertia. So polar moment of inertia is given like that. and very similar to the others, sigma x bending moment stress is given as a is force divided by a, and then proportional to y. Okay. Uh, so my point here is that bar, shaft, beam, the concept is very similar. This is the force. This is the cross-sectional property, and stress is always given as a force divided by A. Okay, force divided by A. And strain, very similar. The strain will be simply delta over L. Delta over L means that, let's say we have a certain delta. Original length was L. So delta over L. Now the torsion, the gamma shear strain will be uh, the this is I'm sorry, this is a little, but it's okay. Uh, we since we have a tau here, okay, because we know the tau equal G gamma. This is a shear strain. Tau actually sigma xy, and the gamma you can say epsilon xy. So we have a G here. uh, shear strain. Well, sometimes gamma is given as a twice of epsilon xy. We need to be careful about that one. But anyhow, we simply divide by g here. We simply divide by e here. Okay. And deformation, how much this delta will be? Delta is simply from here, uh, you can see that force divided by A, this is a stress, and then Young's modulus, okay, you see delta, okay, delta is a epsilon L, and epsilon is given here and sigma. That's why we got this one. We didn't cover in this class since we are studying the strength of material 2 or solid mechanics 2. So delta, it is a very well known that we have a force, length, cross-section, and Young's material property. See, the torsion, when we have a torsion, this will twist. Exactly same. The twisting angle will be a torque. Torque means that the force, and then length is L. The Young's material property will be shear, and the cross-sectional property. Now with the beam is the same. When we apply this will rotate, right? This is a rotation angle. So rotation angle will be given as the moment L and divided by E. I mean I. So the point here again is exactly there will be some analogy between the bar, shaft, and beam. So with the one topic understanding, you will uh, uh, extend it to other concept as well. The material property relate is the Young's modulus and shear, and then beam is also an extension. That's why we have a Young's modulus here. So this is the uh, stresses, but other term, strain, deformation, and also cross-sectional property, there are uh, very has a very common sense. This is the good way of comparison, and then you can understand all together. Okay, so uh, Uh, I'd like to go back a little bit here, uh, and this one, d theta dx. Okay, this is the length. If the length is L, and then we have a twisting moment M, then this will have a angle like this. Okay, uh, angle. This is a theta. So d theta dx, when we apply the pure bending moment at the center, I mean at the end, this will be simply d theta will be a theta, and the dx can be a L, and this will be a moment, uh, EI. Uh, I should have explained this one before. But anyhow, this is the theta and moment L and EI. Okay. Again, this is very similar to the extension. When we apply the force, we have how much the delta here. So delta will be the force L and EA. So you can see that there are pretty much same analogy between each one-dimensional structures. So it's not that difficult to remember, but you should remember this. Well, in physically, say theta or delta, delta will be proportional to F. It is very obvious. And delta will be proportional to L. Sure. Now, inversely, now E is very much stiff. So stiff would not deform. So it's inverse. If A cross-section is big, the deform would not happen. So this is a inverse EA. Same for the bending. Bending proportional to M and L, and the inverse proportional to E and I. Okay. Now, with all this understanding, this is the also cover the force in beam theory, the force we apply is the moment, and equilibrium is the moment, y, uh, sigma x and dA, and the stress is the strain and Young's modulus. This is a material property. And now the deformation is that this strain is given as what? Y dx d theta. Okay. So deformation condition is that 1 over r curvature is given as the d theta dx. So deformation can condition can be sometimes, okay, this is a restriction. This is a deformation condition, and this is a moment to be applied. This is the Young's modulus. So as you can see that the stress will be given as the moment. Uh, always try to remember force divided by A times Y. Well, this is the one. Okay, now there's a minus there. Now, of course, when we drive this one, the material of the beam is same as the Young's modulus, but this can be many different material, layered material. This is a advanced topic, but very important. Okay. So anyhow, this is the all the analysis flow in case of a beam theory. So this flow will be the exactly same as for the general solid mechanics. So this is a stress level and then it should be length and strength. Strength is given as a sigma yield. Because we have only one stress, we don't have to consider many multi-axial stress, but here this much stress uh, caused by the moment and in this cross section, proportional y should be less than sigma y. Okay, so we again the double checked all this 351 flow chart will be applied to beam theory as well. Okay, uh, now combining all these deformation here again, how much angle? This is the angle, right? This is the angle. How much you rotate? This is a theta. So theta is what? Theta is simply moment L and E and I. I is the moment of inertia. So this is the deformation. Actually, this is again we combine all of these. This is the what we get. Actually, d theta dx can be that is 0 and L0 if this is a constant moment. Okay, so this is the one. Well, this is the same one as we already mentioned. I was gonna say just the repeat of these equations for the beam and torsion and also bar extension. Okay, now we have a very important a case uh, where the beam is connected. See, the beam simply like this, we have a moment, and this is the moment of inertia I, uh, and we know how to calculate. This is the angle, right? This is the what we learn. Actually, this theta is the same as this rotation. This is the theta. This is the theta, and this is the theta. Okay, this is the very important. I should emphasize that one in the previous. Okay, I'm gonna go back. I'm gonna go back here. It's not quite shown here, but whatever angle, for example, well, this I would say the if it is clamped, this much angle will be no, I don't want to use this one. Okay, I'm going to use this one. So d theta will be this theta, and d theta will be the same as d theta. Okay, the reason we mention d theta is that the theta may vary over the length, meaning that this, the theta we can vary along the length. But here we apply the constant moment and theta, the rate is the constant. So always the rotation here. So this can be a theta zero and this is a theta zero when moment is a constant. Okay. So moment constant, and this is a theta and this is a theta. Okay. I should emphasize that point. Okay. So, now, again, this is an important the case where we consider the beam stresses. Very simple case, but very important. Say we have a beam, two beams now, two beam. The first one is the E1 I1, two different beam, two different lengths. Okay, the length is different, and the Young's modulus is different, and the cross-sectional property is different. So these two beams are connected, and then we apply the moment M. Now the question is there: how much will deform? How much will rotate? So when we apply the moment, what will be the theta? Okay, this is the one we like to drive. Well, it looks a little bit complicated, but relatively very simple. The reason is that when we apply the moment by the equilibrium, there will be a reaction moment as well. So this moment and this moment will be the same. And even this cross section, if we cut this cross section, there will be a moment, there will be an unknown moment, but from the equilibrium, we can easily see that there will be a same moment as that one. And also the other section, there will be M. Well, this M and this M, there will be a the negative sign, this up here. So simply, this is an action and reaction. The reason we divide this way is very obvious. This one, okay, this moment and moment, the theta angle, theta one, relative to this section, okay, relative to this section, rotation of this is a theta, relative to this is given as like this. Moment L1 and E and I. And same here, when we apply the moment with respect to here, the theta 2 with respect to this one, okay, will be moment and L2 and E2 and I2. Okay, this is the equation from on the left beam, left hand side, and this is the right hand side. This is the beam in series. So you can simply see that this guy at the cross section, this is rotating here. Now this is the rotation with respect to this plane, but this one will be rotated here, rotate this much. So this is a theta 1. And then this will deform like this. So simply theta 1 plus theta 2. This is the theta uh, at the cross section on the right hand side. Okay. So the moment and moment will be the same, and this will be the terms we need to add. Now, the this is called beam in series, and the other case, another case is that the beams in parallel. Okay, in parallel, say we have a uh, clamped on the left hand side, on the right hand side, we have a same as this one, E1, I1, L1, E2, I2, and L2. Now, instead of applying to the end, we are applying the moment at the center, at the connection point. See, we apply the moment is here. So actually the moment we apply will be divide into a two part. One is the moment one goes here, the other moment goes here. So total of this moment will be the M which we are applying. But we do not know what is M1 and M2. But what can we can see is that we just assume there is a M1 and there will be a M1 reaction. And M2, there will be M2. Okay. Now, very important point. Then how do we know M1 and M2? We don't know yet, but what we know uh, is that the this guy, this will rotate. Okay, let's imagine this will rotate like this. Okay. and this guy will rotate. Bu- 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 this will rotate like this, right? I like to draw like this. So this rotation with respect to this one, and this rotation with respect this is all the same. So in other words, the moment, I mean the rotation angle by the M1 and rotation angle by the M2 will be the same. So this guy on the left-hand side, due to the M1, we can have an equation. The angle on the right-hand side, angle is given like that. But very important point is that the theta 1, theta 2 equal same as the theta, which will be observed by this at the section, the cross section where we apply the moment. So simply from this, uh, uh, we have this and we have this. This is a little bit more complicated than beams in series, but as you can see, this is the one condition, right? This is important. The M we apply, it will be divided into M1 and M2. We don't know what is M1 and M2. Now we do know this one, second equation and third equation. Okay. Now, very importantly, this is a geometric equation. So the number of equation we know is the 1, 2, 3, 4. What is the known? What is the number of an unknown? Unknown is the M1, theta 1, M2, theta 2. So we have a four unknown and four equations. So this is can be a solvable. Anyhow, the we combine this, we get this equation. So moment and theta, and simply get E on I1 divided L1 and so on. Okay, so this is the four equation, we get this. So moment theta and this, and this can be a moment, okay, and divide by the theta reverse like the L1 by the E1 I1 plus L2 E2 I2. Okay, so this is the series, and this is the parallel. Okay, this is the kind of stiffness. See, this is a moment, the force and deformation. And this is the, what do we call? Stiffness. Stiffness, what it means, the always a force is like the spring constant. Like this spring, we have a F and we have a, uh, say, a delta. Okay. So K, always F equal K delta, right? So force and deformation, this is a proportional coefficient called stiffness. And same here, this is a force and this is deformation, this is the stiffness. And this is the moment. This is the same as this one. This is a moment, and this is a deformation, and this is the stiffness. So depending on this series or parallel, as you can see, we can get the stiffness. We can get the how much angle. Okay, in this case, the theta, and this case is theta, where we apply the moment. Okay, so this is the one very important application of a beam theory, beam stresses, uh, and you need to practice. You need to understand this one. Very importantly, this will be certainly one of a question we need to prepare for the final exam. It's early to say the final exam, but this is the one you need to consider that. Well, as I announced, we're not going to have a midterm, okay? Uh, the But final exam, uh, in the last week of the this semester, sometime the first week or second week of December, we will have a final. And then remember, this is the very important subject. Okay. I will give you a little bit of a tip. What kind of we can have many different types of cases. Something like this, and then you can have these things. Or you can have this clamp. You can apply the moment here, or you can apply the moment here. Any place. So we apply the moment, and we should know how much it rotate here, the theta. So moment and theta we apply. I mean moment apply, we can get how much deformed. Well, I think some of you already noticed that let's say we have a spring and the small two spring K1 and K2, and this is the F. Now, how much did we observe here, the delta here? How do we get this one? See, simply the force applied here will be the same as here, the reaction, and the force will be the same. So this one, this is all same F. This is F, and this will be the F. So say F K1 plus K1 delta 1, and this one F will be a K2 and delta 2. What does it mean? K1 and delta 1, delta 2. Delta 1 is the deform. This spring will deform. And delta 2 is the spring will deform with respect to this point. So actually the delta will be simply delta 1, which will expand this one, and then expand this one. So delta 1 and delta 2. So delta 1 plus delta 2. And delta 1 will be a K1F from here. And the right-hand side, you will have a F, K2. Now, F and F will be the same. So you can see F, K1 and K2 like this. So in terms of stiffness, what do we do? This is a stiffness. F equal delta and stiffness. What is that? 1 over K1 and plus 1 over K1. Oh, sorry, K2. So this is a stiffness. Well, now you can see this is very well known. Stiffness in case of a series is a spring. So compared to this, now this one and that, moment and theta, pretty much same as the spring under series. And the same for the spring in parallel, like this spring, one spring and another spring, you apply the F. See, this one is K1 and K2, and this guy will deform. I would say delta 1. Sorry. And this one will be a delta 2. And see, we don't know the F1 and F2, but we do know F equal F1 plus F2 because this external force will be the sum of the F1 and F2. And then F1 will be simply K1 and delta 1, and F2 simply K2 and delta 2. Now, very important point is the here, this delta 1 and delta 2 will be the same. So this delta 1 equal delta 2. So this is the geometric constraint. And so the F1 and delta 1, F2 and delta 2, we have a four unknown, but we can see you can see that we have a 1, 2, 3, 4 equation. So there's no problem to solve this one. Obviously, the F will be given as delta and K1 plus K2. If we solve this one, we will have this. So this is the spring for the parallel, and this is a spring in series. And this is the one similar to the this case. So this is the, I would say, we can say the spring constant in the beam. So this is uh, the case. Okay. So what I'm trying to do actually, I'm trying to have some bridge between the simple concept and the concept, current concept, beam. So this is the very simple concept, and then result you already know, and this is a clear connection of same concept, and is very easy to remember this and remember this. Okay. But this, application-wise, this can be a little bit more complicated, but the understanding of a concept and this will be pretty much same as a spring. I hope that this help you to understand all the beam deformations and the also stresses analysis. So rather than just try to understand beam theory, shaft torsion theory, and beam theory separately, rather than understand separately, try to understand them together. And conceptually, they are same. That's a physics. Uh, even in the all kinds of force and deformation and all this kind of I would say mechanics, we can observe these types of analogies. So that's the one very important message I like to emphasize. Okay. Well, there will be a chapter 11, beam theory 2. Now is a deflection due to bending. Deflection. Okay. Deflection. The deflection we cover so far is what? Is under constant moment, right? This is the deformation or deflection. But now is a section is the uh, again, cannot emphasize importance uh, too much. So it is so important. Beam theory, deflection due to bending. So deflection due to bending, moment curvature relation, actually the force equilibrium and governing differential equations and boundary condition and beam problems. Uh, and this is the subject we will cover. And this is the core, real last essence of this uh, strength of material or solid mechanics course. Okay. While the studying this subject, actually, we start with the beam theory we just covered. Okay, we just covered. I'm gonna just have this one and then close today's class. Okay, so now, okay, don't forget what we are trying to do is that try to get the deflection, okay, Vx in general, not just the pure bending, but this can be uh, can deflect under many different load. Okay, this is the what we're gonna have. See deflection of Vx, okay, and then this is the theta and this is the theta. We already consider that. Now this theta, see r d theta, okay, r is the simply like this, and d theta or theta. You can consider d theta or theta. If this is very small, you can say d theta. Okay, so this is the theta. Now, this is the dx. Dx means that looks like the this one, right? This is the dx or x. Uh, well, you can say this is a small, okay? Very important assumption is that this is the dx and this is the r d theta. This one and this length is strictly speaking, this is not the same, right? This is obviously looks a little bit longer than this. But beam theory, we are we consider case where is a very small deflection. Small deflection doesn't mean very small or under certain constraint. This R d theta is the same as the R d theta and dx. This is already we assume in previously previous section. Now, so this is the we already know, and this is the what we already know. This is the one very importantly. This is the one we uh, introduce. What is that? dvdx. Okay, here we had a theta. Okay, here we had a theta. Now, as you know, this is a beam equation. Beam equation like the Vx. What is the tangent here? Tangent, we know that dv dx is always what? Tangent theta. This is what we know. Okay, this is what we know. Okay, this is nothing new. You already know you have a curve, you have a tangent. Okay, the tangent given as a tangent theta. So theta is the uh, over here is a tangent. That tangent will be the same as these cross-sectional rotations. Okay, now we assume small deformation. Small deformation is the one we are covering right now in beam theory. So in small deformation, tangent theta is the theta. It is this is a very well known that, right? Tangent theta is a cosine theta and sine theta. And small theta, this is the one and this is a theta. So tangent theta is approximately theta. Now, with this, dx is rather than tangent theta, we can say theta. Now, d theta dx, get dx d theta, sorry, d theta dx, now we can give it here. Now, twice of derivative of deflection curve. See, this one was the d theta dx in previously. Now with this assumption, okay? With this assumption and small, sorry. This is not the assumption. This is the known. This is not the assumption, but this is the assumption. Small deformation, tangent theta is the theta, and now we have this, okay? So, the curvature is simply second derivative of deflection curve. So EI curvature now, all combine this with this assumption, we have a moment EI double curvature. I mean the second derivative. Okay. So I'm going to write here moment EI curvature or 1 over R. Now this guy is given as the second derivative. I mean, deflections. Okay. Well, easy to remember. Moment EI second derivative. This is the one you need to remember and understand. Okay. Moment and deflection. Moment and deflection, or moment with so it's like the force and deformation. So force and the I would say K X. So this is EI is it looks like the stiffness, and this is the deformation. Is like the spring. The moment, stiffness, and deformation. Okay, so this is the one you need to remember at the very beginning of a beam deflection theory. Okay, so next one we will just go through a equilibrium and the combine this. Equilibrium means that y directional equilibrium. Okay, and then a moment equilibrium combined, we get those two equations. And combining these, we have this. Don't worry, we will go again. Okay, this I'm just browsing what we'll cover. And the okay, this is the same as that. And now combining all these, see, we had this one. So this two equation is coming from came from this two equilibrium because the force will be in equilibrium in y direction and moment will be in equilibrium. So this is one. And then combining this, we have this. What is that? Q is in general, we have a certain distributional load. This is the we call distribution load, and this is the deflection. This will have a deflection. This is the V, and the V will be obtained by solving this uh, the first order ordinary differential equation. Okay, so this is a force and this is the deflection. So this is the final equation of a beam theory. Okay, so we are saying the force of the differential equation. Okay, the reason I'm just browsed this equation is I'm trying to keep you help you to touch this new subject repeatedly. Anyhow, this is the what we like to cover today. Okay, this week, and then well, last week we didn't have a much class, the homework. Uh, uh, well, now we're gonna assign some homework this week. So anyhow, thank you, and this is what we like cover today, and see you next week. Okay, bye.